Hi, welcome to Mathematics with Tom. I am Tom. Today, we are going to diagonalize A. What does that mean? I'll tell you. What that means is we're going to write A in the form of V. This is a capital lambda V inverse. Well, we now know that an inverse matrix exists if the columns of V are independent, and in our homework problems we learned to find the inverse for a 2 by 2 matrix. So we're going to use that property here today. What does this mean? Well, here I'm going to tell you. V is the eigenvector matrix. Eigenvector matrix. Capital lambda is the diagonal matrix of eigenvalues. Now, you might wonder, well, how in the world do you come up with that pattern? Well, let me show you. So let's think about this. So if I take A and I multiply it by the matrix V. So let's just say that A is a 3 by 3 matrix. So we'd have A times, and V, say it has 3 eigenvectors, V1 and V2 and V3. Well, we know that matrix multiplication can be expressed as a new matrix of A, V1, and then the next column will be A, V2. The next column would be A, V3. Now, here's where it gets more interesting because, watch this. If V1 is an eigenvector, then AV1 can be expressed as lambda 1 V1. AV2, well, that's lambda 2 times V2. And AV3, that would be the third eigenvalue times that same eigenvector. Now, this is kind of a strange little arrangement that we've got. And you can't immediately factor these out. But really what this is this is the same as the linear combination of, if I was to write this as V1, V2, V3, and I will write it out big to show you, because notice this. Notice that the lambda 1 is only found in the first column vector. The other column vectors have no lambda 1, so this is lambda 1, 0, 0. The next column, lambda 2, V2, only has a lambda 2 and a V2. There's 0 V1s and there's 0 V3. So this is 0, lambda 2, 0. And likewise, the third column, lambda 3, V3, well, there's 0 V1s, 0 V2s. So that must mean it's 0 V1s, 0 V2s, but there is a lambda 3 with the V3. Well, we're almost done. What do we have? We said that A times V is equal to all that, but now I have this matrix right here, V1, V2, V3. Well, we just said that is the matrix of V. And we just defined that capital lambda is the diagonal matrix of eigenvalues, and right there, that is it. So I could really say that this is V capital lambda. Now, I'm gonna write it this way. Now let's come up here. I have A, V equals V, not VA, V lambda. Assume V is invertible. Invertible. What does that mean? i.e., V inverse exists. Okay, well, let's multiply both sides. So AV, V inverse. This would, now multiply it on the right, so I have to multiply on the right side. So V lambda, V inverse. Well, V inverse is I, and AI is just A. So I have A equals V lambda V inverse. Okay, and there we go. Now, there was a major assumption right there, and that is that V is invertible. Therefore, V inverse exists. Well, here's what happens. Here's the key. For V to exist, or for V inverse to exist, then lambda 1, comma, lambda 2, lambda 3, if there's lambda n, you could extend this out, must be unique, and non-zero. So why is that? Well, first off, the unique part. The unique part means that they're all different values. If any of them are repeats, for example, if lambda 1 equals lambda 2, well, then that means you're going to get the same eigenvector. So if V has a repeated eigenvector, those become dependent columns, and we just learned that dependent columns cannot have an inverse matrix, so they must be unique. What about non-zero? Well, what does it mean to have a zero eigenvalue? Let's just try that. So suppose lambda equals 0 for some matrix A. Well, what does that mean? That means that A minus 0I times the vector V has to equal 0. Well, remember what we said then is that in order for this to work, the whole premise here is that A minus 0I, that means this is, by its very definition, this has dependent columns. Because if it didn't, then the only solution is V itself is 0. But wait a minute, A minus 0I, that's just A. So that just says that A times V equals 0. Well, that means that A is the same as A minus 0I. So A also has dependent columns. So both of these situations have the same matrix. So if A has a 0 eigenvalue, it means that A has dependent columns. All right, so that's always something to keep in mind. Now, before we try an example, there's one more reason. Here's the real power in this. And that is this. If I asked you to find something like A squared, that could be really difficult. But what if you had taken A and diagonalized it? Well, then A would be V lambda V inverse, and we're going to assume that V inverse exists, times, well, A again is V lambda V inverse. Well, what is that? That just says, that's just the this V inverse V in the middle, those will cancel, those are I. So this is just V lambda times a lambda, that's lambda squared, times V inverse. Well, here's the beauty of this. If you take a diagonal matrix, let's just try this. So I have lambda 1, lambda 2, 0, 0. And I multiply it by lambda 1, lambda 2. What do you get? Well, this just becomes lambda 1 squared and lambda 2 squared, and 0 squared and 0 squared, which are zeros. And the beauty of this is if you take a diagonal matrix, in this case lambda, and you raise it to the kth power, well, that just gives you lambda 1 to the k lambda 2 to the k. And of course, you could extend this out for 3 by 3 and 4 by 4 matrices and even further. That's the power of diagonalizing a matrix. In our next example, we'll actually try, our next video, we'll actually try an example. I hope that helps, and thanks for watching.